Imagine an energy source so powerful, so immense, it's literally beneath your feet right now. This isn't science fiction. It's the Earth's own internal heat, a clean, sustainable power that could transform our future. We're about to demystify how this deep geothermal energy can be harnessed to power our homes and cities, revealing its incredible potential. Imagine, for a moment that you are standing on top of a gigantic, slow-burning furnace. It is a furnace of planetary proportions quietly radiating an immense and nearly inexhaustible supply of heat, just a few miles beneath your feet. This isn't some flight of science fiction. It is the simple, rather astounding reality of the ground we walk on every day. The Earth, it turns out, is wonderfully hot on the inside. This internal warmth, known as geothermal energy, has been simmering away for billions of years, a leftover from the chaotic and fiery birth of our world. It is a form of power that doesn't require burning anything, building enormous dams, or waiting for the wind to blow. It's just there, waiting patiently. This incredible heat comes from two principal sources. The first is what scientists call primordial heat, energy left over from when the Earth first coalesced from a swirling cloud of gas and dust, some 4.5 billion years ago. Think of it as the residual warmth from a cosmic oven that has been cooling ever so slowly. The second source is the gentle decay of radioactive elements like uranium, thorium, and potassium, releasing a steady trickle of heat. Together, these phenomena create a staggering thermal engine beneath our feet. The planet's core is thought to be as hot as the surface of the sun, a blistering 6,000 degrees Celsius. This heat doesn't stay put. It migrates from the core, through the molten mantle, and up into the solid crust. Most of the time, this heat is so diffuse by the time it reaches us that we don't notice it at all. But in certain geologically blessed spots, often near the edges of tectonic plates, volcanic hotspots, this profound heat gets tantalizingly close to the surface, creating the spectacular geyser, bubbling mud pots, steaming hot springs that have captivated humans for millennia. The sheer scale is staggering. Heat flowing from Earth's interior exceeds humanity's total energy use several times over. Unlike finite fossil fuels, geothermal heat is constantly replenished by radioactive decay. The challenge isn't a lack of energy, but the ingenuity to tap this vast, subterranean treasure right under our noses. So, how does one go about borrowing a bit of this planetary warmth? The process is surprisingly straightforward, though the execution can be monumental. It begins with finding the right spot. Study satellite imagery, analyze local water chemistry, measure tiny variations in gravity and electrical resistance in the ground. They're searching for underground reservoirs of hot water and steam trapped in porous rock. Some sites are low-hanging fruit. Once identified, drilling begins. Wells can plunge a mile or more. The goal is a pathway for superheated water or steam to reach the surface. A production well brings hot fluid up. An injection well sends cooled water back down. A sustainable loop that can run for decades. In fortunate places, nature does much of the work. People have long used this heat directly, for bathing, cooking, and warming homes. The Romans famed for geothermally heated baths. But the true prize is electricity. When a well taps a high-pressure reservoir, steam rushes up with force. That steam is channeled into a turbine, spinning blades, and a generator, making electricity without a puff of smoke. Turning subterranean heat into electricity isn't one-size-fits-all. Engineers use three main methods. Dry steam, the oldest and most direct method, rare reservoirs producing mostly pure superheated steam. Steam flows straight from well to turbine, beautifully efficient and simple. The geysers operates largely on this principle. Flash steam, the most common today, used where water above 182 Celsius is under immense pressure. At the surface, a pressure drop makes water violently flash to steam. Steam is separated to drive a turbine. Hot water can be flashed again, then re-injected. Binary cycle, the most versatile, works with much cooler resources, even near 85 Celsius. Geothermal water never touches the turbine. It heats a secondary low-boiling fluid like isobutane. That vapor spins the turbine, then condenses in a closed loop. Separate closed loops mean near-zero emissions and far more viable locations. This tech is unlocking potential from Nevada to the plains of Germany, proving you don't always need scorching steam to tap the power beneath your feet. Now, some success stories, and a surprising truth. Section 4. Success stories and a surprising truth. Geothermal may look futuristic, but it has a long, successful track record. Perhaps no country has embraced subterranean heat like Iceland, perched on the mid-Atlantic ridge. Nearly all heating and hot water are geothermal, piped into homes, businesses, even snow-free sidewalks. About a quarter of its electricity is geothermal, helping make Iceland one of the greenest nations on Earth. In California, the geysers, 13 plants, the largest geothermal complex in the world, at peak powering a city the size of San Francisco. The Philippines leverages volcanic heat across its islands, cutting fuel imports and strengthening resilience. Geothermal is not niche or experimental. It's a proven workhorse in more than 20 countries. Solar panels don't work at night. Wind can be still on a calm day. Geothermal runs 24 hours a day, 7 days a week, regardless of weather. It has an exceptionally high capacity factor, often over 90%, comparable to coal or nuclear. An ideal baseload to stabilize intermittent renewables. That's the surprising truth. Section 5, Promises, Problems, and the Path Forward. The case for geothermal is compelling, and getting stronger. Geothermal is remarkably clean. Binary plants emit virtually nothing. It's a powerful tool against climate change. It's domestic energy, reducing exposure to volatile geopolitics. Exceptionally steady power for the grid. Small physical footprint and quiet operation, with plants that can run for decades. The biggest limitation is geography. Conventional geothermal needs the right conditions. Upfront costs are high. Exploration and deep drilling are expensive, and some wells come up dry without policy support. There are localized concerns, including rare small earthquakes from drilling and injection. Hot water can carry minerals and gases like hydrogen sulfide. Modern plants capture and handle these safely. Despite hurdles, the future looks bright. Enhanced geothermal systems aim to create reservoirs where none exist. Drill into deep, hot, dry rock and inject water. If perfected and economical, EGS could unlock geothermal almost anywhere. The path needs research, smart policies to de-risk exploration, and clear-eyed pragmatism. Geothermal isn't a silver bullet, but it's a vital, powerful tool in the clean energy arsenal. Well, yeah, that's where we stand.